Hi, I'm Joe Payne, and I'm going to be talking about state estimation for hybrid systems with uncertain guards. Legged robots often have difficulties with contact, whether it's making unexpected contact or not making contact when it is expected. To account for this, we need a way to have accurate state estimation so that proper control action can be taken. To better understand the evolution of state in a legged robot, we can view this as a hybrid system, which includes both continuous states like position and velocity, and discrete states, such as whether a foot is in contact or not. Briefly, a hybrid system contains a collection of domains with continuous dynamics, guard conditions which indicate when a mode transition should occur, and reset maps which are applied when a guard condition is met. However, in the real world, we will not necessarily have a perfect model of the hybrid system. One source of this uncertainty is in the guard location. An example of this uncertainty would be ground height variations for a legged robot. This will cause variations in the time to impact, or the time that is spent in each of the hybrid modes surrounding a reset. Another source of this uncertainty is in reset maps. This could take the form of differing surface properties when contact is made, or even just different surface normals enforcing different constraints. To adapt these algorithms designed for smooth systems, in this case, the Kalman filter, to hybrid systems, we need to be able to obtain gradient information through hybrid events. We can do this by analyzing how perturbations are mapped through a transition event with guard displacement. To do this, we can examine how the nominal trajectory evolves from its impact time to the time of the perturbed impact. The nominal trajectory will be reset into the new mode. In this case, the reset is identity for ease of depiction, and follow the new mode's dynamics for time dt until the perturbed trajectory reaches the guard. The perturbed trajectory will follow the first mode's dynamics until it impacts, and then the reset will be applied. This can be approximated as the reset of the nominal point plus first order approximations of variations about the nominal reset map with respect to state and time. Taking the difference of these two yields an expression for the post-impact variation as a function of the pre-impact variation and the impact time difference. To determine the solution as a function of only the position and guard displacements, we will need to solve for dt as a function of those two. To do this, we can determine dt by examining it as a distance divided by a velocity. The distance is composed of the initial displacement projected into the guard direction and the guard displacement. The velocity is composed of the first mode's dynamics projected onto the guard direction and the velocity of the guard, if it is time varying. Using the expression for the variation as a function of initial displacement and time, and the solution for time as a function of initial displacement and guard displacement, we see that the post-impact variation is equal to the original saltation matrix plus an additional guard uncertainty term I will call the guard uncertainty saltation matrix. Now that we've derived this guard uncertainty saltation matrix, we can see how it's useful in predicting the covariance update of a system undergoing a hybrid transition with an uncertain guard. Here, the gray vertical lines are sampled guard locations from a distribution, and the black dashed line represents the nominal guard surface. Using this guard uncertainty term improves the prediction of the resulting covariance distribution over only using the saltation matrix. This covariance propagation update is what we will use in the process and measurement updates at hybrid events in the uncertainty-aware Salted Kalman filter. In addition to uncertainty in guard locations, we also have to account for uncertainties in reset maps. There's not a general solution to this for all systems. So the way we handle this is by parameterizing reset maps and taking derivatives with respect to these parameters. An example of a parameter we could use in this case would be the guard normal direction or the coefficient of restitution in a simple bouncing ball example. This update can then be added in when updating post-impact covariances if we have an estimate of the distributions of the reset map parameters. Using these update rules, we now compare the saltation matrix prediction alone to the prediction including the guard and reset uncertainty terms. We can see that the two are the same for the nominal system. In these figures, the blue dashed ellipses represent the covariance predicted with the uncertainty awareness, and the red dotted ellipses are the saltation matrix alone. The guard uncertainty term improves the performance when we're uncertain about ground height, and the reset uncertainty term improves the performance when we're uncertain about the ground angle, which changes the reset map parameters. And using both, when we have both types of uncertainty, also accurately predicts the resulting covariance. Now we consider the use of this covariance propagation in a Kalman filter. For use in a Kalman filter, we use the standard covariance update rules when the state is in a continuous mode. However, when the mean reaches a guard condition, we apply the reset map to the mean and use the saltation matrix, the guard saltation matrix, and the Jacobian of the reset with respect to its fixed parameters to update the covariance instantaneously. Similarly, if a guard is crossed in a measurement update, the reset and saltation terms are applied to the resulting distribution. Here, we can see that the tracking error is notably improved in a simple bouncing ball case when we consider the structural uncertainties. The tracking error for the saltation matrix alone is shown as a red dashed line, and the tracking error considering structural uncertainty is shown as a blue solid line. The improvement can also be seen in more complicated systems, such as a slip hopper with uncertainty and ground height. It should be noted that most of the improvement in error is seen in the vertical directions, as the additional guard uncertainty term is a rank 1 update along the vertical degrees of freedom. So in conclusion, when we explicitly consider structural uncertainties in guard locations and reset maps, we are better able to predict covariances through hybrid events. Using these improved covariance predictions, we get better tracking accuracy in Kalman filtering methods on these systems. Thanks for listening.